half-life for the time, well, for this course, you can delete that. And then down toward the bottom, you can delete integrated rate laws and half-life. And that's the first page. And then the second page, in case you've had a chance to already work. Yeah, Juan, could you, quiet please? I'm old and cranky. On the second page, there are some problems. So if you've already nailed the entire review sheet, that here are some backup problems to take a look at from the backs, from the last of each chapter. Now, there have been a number of questions coming in by email or whatever. What am I doing tomorrow? Okay, the 10 o'clock review tomorrow, I really can't tell you because it depends who shows up, and if it's this very same group, I will find something new to do. If it's a brand new group, we'll probably start at the same place we're starting today. So what I planned for today is the review right here, just to work as many problems as we can, and probably work maybe hour and a half, 2 hours, and then we'll pick up tomorrow. If there's still stuff here, we'll pick up there. If we complete it all, then we'll see who shows up tomorrow and what your needs are, or whoever it is, what their needs are. Okay? Now, this is fairly informal, that if you decide you know all this stuff and you're wasting your time, I mean, at any time, just get up quietly and take off. Don't feel like you're a prisoner here. It won't hurt my feelings. Now, let's just go through it because you may be way ahead of where other people are. So, anybody else want to move down to prime real estate here before we start? Okay, this is the review for the final that I put up there, I don't know, a week or two ago. So either you have a copy, or can you read this okay? And if you're way in the back, everybody see it okay? Read it okay? Okay, good. Okay, then what I should do, pardon me, cough drop already. What I should do is I should make it smaller and then tell you my husband's an optometrist and give you his business card. Okay, all right. How many compounds of the ones listed below have hydrogen bonding? Now, notice the wording on that. It doesn't say which one. I got suckered into that when I was working through the key the first time. It says how many of them. And so what we have to do is it really makes you know this a little bit better. Instead of just spotting one, you've got to be careful of all of them. Okay, if we have hydrogen bonding, obviously we need a hydrogen. What else do you have to have? N, O, or F. And there's another stipulation. The hydrogen has to be directly bonded to it. Okay, so I take this organic material. It's called an amine. Yes or no? Yes. Okay, and if you don't see it, slow me down. Don't just write answers. Understand it. And you'll save a lot of study time.
See what again?
Okay, this one right here, that, can it hydrogen bond? Yes, because the hydrogens here are directly attached to that nitrogen, one of the big three, in electronegativity. Okay, now, let's look at this middle guy here. Now, this may be problematic for you, but a nitrogen is going to be attached to three things. So this middle one, oops, I didn't get enough. C2, let's see, CH2, excuse me. CH2. Here's what the middle one would look like. Okay, do you see how on the very first one, it's really, they're all cousins of each other. The very first one had a nitrogen, it had a hydrogen, and then in the second one, we still have one hydrogen, but we substituted this ethyl group, this C2H3 group. So, can this hydrogen bond to itself? Yes or no? Sure, because you still have an NH. Are we okay on the second one? Okay, on the third one then, what you have CH2, excuse me, CH2, CH3, CH2, CH3, CH2, CH3. Okay, so what have we done as we go down the line? We've substituted for all three. And do you see how these are all cousins of ammonia, the one we're more familiar with? Okay, this can certainly hydrogen bond to itself. Okay, then in the first one up there, we only substituted for one of the hydrogens with an ethyl. Okay, in the second one, we've substituted two ethyl groups for hydrogens, but we still have an NH. But by the time we get over here, all the hydrogens have been substituted for. Okay, so you told me, yes, this can hydrogen bond to itself. Yes, this can hydrogen bond to itself. Can this one? No. Okay, so what's the grand total for the number that can hydrogen bond? 2. So the answer is C. Okay, we good? All right, onward. List the compounds in decreasing boiling point order. Okay, now, in Chapter 11, the name of the game was Intermolecular Forces of Attraction. Let's fire through them. Let's consider 4. Now, in your book, they didn't consider the ion. Okay, now remember, when you look at a compound, it's going to be a 3-step process. First, you're going to decide, is this compound ionic or is it covalent? Okay, if you decide it's ionic, your work is over because you know it's ion-ion attraction. Okay, if it is covalent, you got to decide, is it polar or is it non-polar? Okay, then you got to know the order of strengths. And in Chapter 11, the stronger the attraction, the higher the boiling point. Okay, remember that whole series? Now, out of those 4 that I just mentioned, well, out of the 3 compounds, let's go through the types of attraction here. Okay, what's the strongest attraction of all? Ion-ion. What comes in second place? Hydrogen bonding. Okay, that's really Chapter 12, because in Chapter 11, what I did then, yeah, you're technically correct, but in Chapter 11, I stuck with just stuff attracted for itself. Okay, if you talk ion dipole, you got 2 kinds of substances, and that's more Chapter 12. So I disagreed with the author, and I kept that for Chapter 12. Okay, so in this chapter, our attraction, ion-ion is stronger than, who did you say came in second place? Hydrogen bonding. Who comes in next? It's been a long time ago, hasn't it? Dipole. You can say dipole, dipole, as the book does, or you can say dipolar. Okay, and just, you can shorten it to one word. And then dead last, dispersion. Okay, and remember, everybody's got dispersion. Okay, but what dictates its characteristics? The strongest that it has. Okay, now, we talked about boiling point, melting point, blah, 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 blah. Let's go through. Now, what we've done so far, we've reviewed our kinds of compounds, the 3 of them, and then we've reviewed the 4 kinds of intermolecular forces of attraction. Okay, let's fire through. For the highest boiling point, let's forget this problem for a moment. For the highest boiling point, do we want the strongest or the weakest attraction? Strongest. For the highest melting point, do I want the strongest or the weakest? Strongest. Okay, for the highest surface tension, do I want the strongest or the weakest? Strongest. Okay, for the highest viscosity, do I want the strongest or weakest? Strongest. Okay, for the highest vapor pressure, do I want the strongest or the weakest? Weakest. Good, good, good. Okay, let's see. What else was there? Heat of vaporization. For the highest heat of vaporization, do I want the strongest or the weakest? Strongest. Okay, now there's 2 phrases I said people tend to mix up. One is vapor pressure, well, that was another one, rate of, here it was, rate of vaporization or evaporation versus heat of vaporization. Because the rhythm of the word sound, let's be sure we've got that clear. Okay, rate of vaporization, okay, or also called rate of evaporation. Okay, the weaker the forces, the faster it escapes. It can get away from its neighbors. Now, heat of vaporization is what it costs you to get it to vaporize. So, stronger attraction, higher heat of vaporization. Okay? Stronger attraction or weaker attraction for highest heat of fusion. Strongest. Okay, heat of fusion. What's another word for fusion? An everyday word. Melting. When you see fusion, it's the same as melting. Okay, so heat of melting. It's how much it costs you to melt it. Well, think about it. On a molecular scale, here you're in the solid state. We have just a little bit of vibration. We go into the liquid state, rolling and tumbling. Okay, the stronger the attraction, the more heat it's going to take you to break some of those intermolecular forces of attraction and let them roll and tumble over each other. You're kind of setting them free. Okay, and then if you vaporize, you totally set them free into the gaseous state because there's no attraction, or essentially no attraction at all in the gaseous state. Okay, let's go back here. Now, it says, list the compounds in decreasing boiling point order. Decreasing. Okay, so we want the strongest one first. So we got to go through here and let's do this. It's this three-step process. I've got this stuff right here. Propane is what it is. Okay, is it ionic or is it covalent? Covalent, because it's what? A hydrocarbon, isn't it? We know all hydrocarbons are covalent for starters. We also know all hydrocarbons are what? Polar or nonpolar? Nonpolar. Now, tell me, what kind of attraction does this propane have? Dispersion only. Okay, so a lot of you, you're like deer in the headlights here. It's been a long time here. Okay, here's our three kinds of compounds. You learned that or heard about it first in 1311. Okay. Chapter 11. This can go either way. Remember, hydrogen bonding is just a very special case of the dipole-dipole, just stronger. But the mechanism is identical. But nonpolar covalent only have dispersion. Okay, and then we already talked about what's the strongest. Okay, so if I were starting this problem, let me just put my three carbons in a row. Okay, that, first of all, I think to myself, if I made up a table, and if you're really desperate, make up a table. Compound, fraction. Okay, and it should come back in time, but this is in ancient history right now. Okay, I've got propane, and I've been too lazy to put in all my hydrogens. A lot of organic chemists do this, just a line, it means the hydrogen's hanging out there. Okay, so we said, it is nonpolar. And if it's nonpolar, it has only what kind of attraction? Dispersion. Okay, now let's look at the second one there. I have argon. Now, technically, that's not a compound. but we treat all of those, it's a noble gas over there, we treat it as nonpolar, okay? And that means what kind of attraction does one argon have for another argon? Dispersion. Okay, and then we have okay, CH3, a methyl group hanging on the end, and then I have this CN group right here. What kind of compound is that? Is it, first of all, ionic or covalent? Covalent. Carbon compounds are covalent. Hydrogen compounds are covalent. Now, is it polar or is it nonpolar?
Non-polar.
You got the CN hanging out at the side. It's going to be polar. Okay, so this is going to be polar. Okay, here, a little more info. If you saw a Lewis dot, see that thing out at the end? It's going to make it polar. Okay, because nitrogen almost always has this lone pair, which means if you got a nitrogen in your compound, unless you're talking ammonium, NH4+, if you've got a compound, neutral, I bet the ranch that it's got a lone pair, which is going to make that part of the molecule polar. Okay, so it's polar. Now, what kind of attraction does it have? Does it have just the run-of-the-mill dipolar, or does it have hydrogen bonding? It just has dipolar. Okay, so of those three, who has the highest boiling point of all? The last one. So, CH3CN. Okay, now I would work this out to the side. I would not try to sort through that because they can mess with your mind real easily that way. So we've got this one out at the top, but at this point in time, we might just get lucky, and we would here if you're a gambling person. This is the only answer with this one coming in first place. But I wouldn't do that. I wouldn't gamble on the final day. I would go through and look at all of them. Okay, now, we have here dispersion, dispersion. If things have the very same kind of attraction, what breaks the tie? Size. Okay, so as far as size, okay, who's going to come in second? The propane or the argon? Propane. And then argon. Okay, so we look. Where are we here? Yes, that looks good. Answer A is still in great shape. But if you gambled, you would have been right. Because once you picked the first one, and they weren't very clever, they didn't show us two with that as first place. Okay, are we good on that? Okay, let's move on. Okay, in liquid propanol. Now see how many organic structures. A lot of you begged for us to do chapter 20. No, not really. We did not do chapter 20 formally, but we're talking about a lot of organic things as we go through here. Okay, see this little OH group hanging out at the side? Alcohols have an OH group. Okay, now, we want to know which intermolecular forces are present, and that means all. Okay, so we look at it. First thing you should ask yourself when you see a compound, ionic or covalent? Covalent. Then, is it polar or is it nonpolar? Polar. Alcohols are polar. Okay. Why isn't that an Arrhenius base? I see an OH group. Why isn't that an Arrhenius base?
That's a metal.
Doesn't have a metal. Okay, it's an alcohol and it's got a bunch of carbons on it. Okay, so let's just think. What kind of attraction does it have? Does it have ion-ion? Well, of course not. Does it have hydrogen bonding?
Yeah.
Yes. Okay, so it's got hydrogen bonding because of the OH. Okay. Do we list others? If you say hydrogen bonding, you want to go ahead and say dipolar. Okay, because if something has hydrogen bonding, just assume we're going to call that dipolar as well. Will it have dispersion? Yeah, because everybody does. Okay, so we've got to look. okay, it looks like answer A again, because dispersion, hydrogen bonding, and dipole forces, all three. Okay, onward. Choose the molecule or compound that exhibits dipole forces as its strongest. And that means only, really, doesn't it? As the strongest intermolecular force. Okay, so we got to find something that is polar. So we'd like to go through.
Not do. I mean, you can cancel out hydrogen bonding.
Okay, let's see. That exhibits dipole as its strongest. So yeah, if it's got hydrogen bonding, trash it. Okay, now, if it's dipole, we got to be polar, right? Okay, what about answer A? No, because something just bonded to itself is always going to be non-polar. So A goes out. Let's look at B. Okay? What we really have to do here to know this is we've got to know the Lewis dot structure. And likewise for C, and likewise for, in fact, for all of them, really, we've got to know Lewis dot structures. Let's just fire through one. I have dioxide. If I use S is equal to N minus A, and I did one of these for you. This is back chapter 9 or 10 in your book. You need to review. We're going to assume nobody's violating the octet rule here in this one. Although sulfur can, if you have a fantastic memory, but it's not going to violate here. So sulfur needs how many electrons total? 8 in its outermost shell. And then each oxygen needs how many in its outermost shell? 8. Okay, so there's 24. Okay, available. This is where you look at its position on the periodic table. Sulfur comes in with how many? 6. Each oxygen comes in with how many? How many? 6. Okay, that's 18. So the number that we share, okay, remember this little formula? It's really handy. First of all, it's only for covalent things, and it's only for the valence shell, meaning the outermost shell, because that's where the action is. This is total needed in the outermost shell. This is total available that it comes with in the outermost shell. Okay, so we run through this. So our number to share is going to be what? 6. Okay, who's our central atom? Sulfur. Okay, I'm going to put an O and an O. Remember, Lewis dots don't show us shape. They just, it's bookkeeping. Now, I've got 2 bonding sites, but I've got to share 6 electrons. What's the solution for this dilemma? My God, you blow all your electrons over on one side. A triple is, I mean, that's an answer, but not a good answer, because if I blew all, if I blew them all, I have nothing to bond with that poor oxygen out there. It'd be left out in the cold. Let me just, okay, if I do singles, that's not going to cut it, is it? Because that's just sharing 4. What shall I do?
Put a single on one side and then double on the other.
Perfect, Eric. A single on one side and a double on the other, and it doesn't matter which one. Okay, and then I go ahead and give everybody an octet that needs it. Okay, how many more electrons does this guy need? How many more does it need? It has access to 2, so it needs how many more? 6. Okay, now, I went ahead and gave this guy 2 pairs. So look at that. It feels like it has access to 8. 2, 4, 6, 8. This guy now has access to 8. 2, 4, 6, 8. The octet rule. What about sulfur? What else does it need? A lone pair. Now, once I do that, I go, okay, it's got 1, 2, 3 things around it. Then I think of Vesper. 3 things. Remember trigonoplanar? Polar, nonpolar. Polar. But see, you would not know that if you didn't go through all that hard work, because you wouldn't know it had a lone pair on it. Okay, you might just think sulfur's in the middle and oxygen, oxygen, linear and nonpolar. Wrong. Okay, so SO2 is still in the running for dipole-dipole. Okay, in fact, if I were a gambling person, I would quit working there. Because it says, choose the molecule or compound that exhibits dipole-dipole forces as its strongest intermolecular force. Well, the only thing that can beat out dipole-dipole is hydrogen bonding. And if you scan that, I mean, we're not interested in that. All we want is dipole-dipole. So, bingo, we got our answer. But, just for grins, if we did the Lewis dot of BCl3, the next one, and I would do it this very same way, however, you would have to remember boron from that 3A family violates the octet rule for us, always, always, always. Okay, let's think about violators. Hydrogen always needs how many? 2. Violates, always, always. It's always means it's on the outside or the periphery. It could never be a central atom. Okay, if I have beryllium from the 2A family and it's in the middle, and they don't give that one there, but this is a classic too, like BeCl2, and they tell you it's got covalent character. Okay, beryllium as a central atom settles for how many? 4. Violates for us, always, always. And then if you're from the 3A family, like boron or possibly aluminum, it settles for how many? 6. 6 electrons. There's a pattern here, if you see it. Hydrogen's from the 1A, settles for 2. Beryllium's from the 2A, settles for 4. You see a pattern? Whatever its family, times 2. And then boron, and only the first members here will do this. Boron and aluminum. 3A family, settle for 6. And I don't think you all in this course will run into it on the high side. Number 10, you had it in 1311, but I don't recall ever seeing one here. Okay, so SO2 is looking good. Now, if I look at this guy, though, now that's Lewis dot, so it doesn't tell us shape. See, it violates the octet rule, so there's no hidden lone pairs. Besper theory, then. I got 3 things around it. What's my orientation in space? Trigonoplanar. Polar, nonpolar. Nonpolar. So it's not in the running here. This one's a hard way to earn 3 or 4 points because you got to do lots of work. Okay, ammonia. Remember how I said almost all of the nitrogen compounds are going to have a lone pair? Not 100% of the time, but a lot of the time they do. Okay, polar or non-polar? Polar. Well, hey, it's going to have dipole.